Welcome to the bridge course in statistics. I'm Li Enpin, and my advisor is Li Junyi. This course will be about 20 minutes long. I will cover a few basic topics in statistics that will hopefully provide you with a better introductory experience for your university courses. The first topic I will discuss is binomial distribution, which extends from high school to university level concepts. Next, building on the foundation of the binomial distribution, I will introduce the normal distribution. Finally, I will touch on the central limit theory and briefly explain its unique phenomenon. I hope this special phenomenon will spark your curiosity and lead to more in-depth discussions with your professor in class. Without further ado, let's dive into the first topic. To define the binomial distribution, we have four conditions. First, there are unidentical trials. Second, each trial has only two possible outcomes, such as success or failure. Third, assuming the probability of one outcome is p, then the probability of the other outcome is 1 minus p. These probabilities don't change across trials. For instance, if the probability of success is p, then the probability of failure is 1 minus p. Fourth, the trials are independent of each other. To give you a more concrete idea, let me illustrate with an example. Assume we have a binomial distribution for a dice rolling experiment, where we roll the dice 4 times. Here, we define the success event as rolling a 3 or a 6. In other words, the probability of success is 1/3, and the probability of failure is 2/3. Now, how do we calculate the probability of achieving success once? First, we need to decide in which of the 4 trials the success will occur. We have combination for 4 outcomes and pick one choices for this. Let's say we pick the second trial to be the success. And the others to be failures. For this situation, the probability of the event occurring is 2/3 multiplied 1/3 multiplied 2/3 multiplied 2/3. Since we have combination for 4 outcomes and pick one choices, and each choice has this probability, summing them gives us the total probability of achieving one success. Of course, if we have X successes, we can construct a similar expression based on the previous reasoning. This expression is not difficult, but I want to use it to introduce some symbols and their conventional meanings in statistics. In statistics, uppercase letters typically represents the variable itself in the literal sense. For example, X represents the number of successes. Lowercase x represents the value of X. In our example, X could be 0, 1, 2, 3, or 4, indicating the number of successes. The notation for the probability of having one success is and from our previous calculations, we can derive which represents the probability formula. These are common symbols used in statistics. Now, I calculate the probability for each possible value of the variables and plot them in a bar chart. It will look like the chart here. The bar charts here represents the binomial distribution I want to introduce. To clearly explain the internal structure of the binomial distribution, we usually use a specific notation to represent it. Now, I will briefly explain the meaning of these notation. First, x represents our random variable, which is the number of successes mentioned in the problem. B denotes the binomial distribution. N represents the number of trials. P is the probability of a specific outcome, such as the probability of success in our example. In the binomial distribution, there are some commonly used statistical measures that we learned in high school. Let's review them. The expected value, also called mean, is calculated as N multiplied P, which is the number of trials multiplied by the probability of success. The variance is calculated as N multiplied P multiplied 1 minus P, or it can be written as N multiplied P multiplied Q, where Q equal to 1 minus P. The standard deviation is the square root of the variance. Next, let me introduce the normal distribution. Although the normal distribution has a specific function, its meaning is relatively complex and is rarely used in solving problems in introductory courses. As a result, I won't go into detail about it now. Instead, let's look directly at its graph. The graph of a normal distribution looks like a bell curve, the value corresponding to the center line of the peak, which is the ax of symmetry, is the mean. As the standard deviation increases, the graph flattens out. As the standard deviation decreases, the graph becomes more peaked. This signifies that the standard deviation measures the dispersion of a set of data. The larger the value, the more dispersed the data, and the smaller the value, the more concentrated the data. Another important point to emphasize is the two types of probability distribution: discrete random distribution and continuous random distribution. The binomial distribution belongs to the former, while the normal distribution belongs to the latter. For discrete probability distribution, the probability is represented by the height of the bars in the bar chart. For example, in the previous bar chart, we can determine the probability of different variable values by the height of the bars. However, in continuous probability distribution, we cannot find the probability at a specific variable value. We can only calculate the probability over an interval of the variable by finding the area under the curve. Let's do a simple exercise. For the given graph, if I want to know the probability that x lies within the interval of the mean minus the standard deviation to the mean plus the standard deviation, that is, this area, which is approximately 0.6826. How do I know this? Let's find out. As shown in the figure, there are three commonly used probabilities in the normal distribution. We just mentioned that the normal distribution is symmetrical around the mean. When x is within one standard deviation of the mean, the probability is 0.6826, meaning that the area within this interval is 0.6826. Similarly, when x is within two standard deviations of the mean, the probability is 0.9544, meaning that the area within this interval is 0.9544. when x is within 3 standard deviations of the mean, the probability is 0.9972, meaning that the area within this interval is 0.9972. These three numbers are very commonly used and important. In later examples, I will still write these numbers down, but I encourage you to memorize them if you have the time. Next, I'll introduce how to use these three sets of numbers with a case study. Let's assume a country has a population of 10 million people with an average weight of 62 kilograms and a standard deviation of 6.7 kilograms. Assuming this distribution is normal, how many people approximately have a weight between 48.6 kilograms and 55.3 kilograms? First, let's observe the relationship between the numbers 48.6 and 55.3 with the mean and standard deviation. Upon inspection, we find that 48.6 is the mean minus 2 standard deviations, and 55.3 is the mean minus 1 standard deviation. We need to calculate the probability for the interval from the mean minus 2 standard deviations to the mean minus 1 standard deviation. This is the area I've shaded in the graph. How do we calculate this? We first build this interval into two parts. One is half the area within 2 standard deviations of the mean, as I've shaded, and the other is half the area within 1 standard deviation of the mean. Subtracting the latter from the former gives us the area we want to find, like this one minus this one. According to what we've just learned, we use the values 0.9544 and 0.6826 for these calculations, respectively, to find the area of the target interval. Finally, we multiply this probability by the country's populations to get the desired answer. The number of people whose weight is between 48.6 kilograms and 55.3 kilograms. This is a very common application of the normal distribution. Last but not least, I want to briefly explain the central limit theorem, which was the most fascinating and interesting theorem I encountered when I first studied statistics. The theorem states that when the sample size is sufficiently large, the distribution of the sample mean will tend to be normal. Let me explain with an example. Assume we draw 50 samples from the initial binomial distribution example. The probability of drawing a sample with 0 success is 16/81. The probability of drawing a sample with 1 success is 32/81, as shown in the bar chart we drew earlier. If we calculate the sample mean for each of the 50 draws, we call this the sample mean x bar. If we keep drawing 50 samples at a time and calculate the sample mean each time, we can plot the probability distribution of x bar. As shown in the figure, the resulting plot looks very similarly to a normal distribution. Remarkably, even though we are sampling from discrete probability distribution, the distribution of the sample means forms a shape that resembles a normal distribution, which is a continuously probability distribution. This is the fascinating part. Could this be wrong? The answer is no, because it can be proven. Additionally, it can be shown that the mean of this normal distribution, the central value, is equal to the original mean, n multiplied p. The variance is the original variance divided by 50. I won't go into the details, but it is indeed a fascinating and interesting phenomenon. If you want to understand why this cool phenomenon occurs, then take the statistics course. Today's lesson ends here. Thank you all for watching.